Welcome back. We are continuing with our study of vectors. Now, when we looked at vectors the last time, we did so in the context of these coordinate axes, as we call them, right? And back then, we referred to them as x1, x2, x3, on the basis of the fact that we very well understood what this meant. We could easily connect it with our notion of coordinates and so on. And it was in that setting that we then spoke of our vector, right? We're going to return to this idea, but do it a little differently now. In particular, we're going to introduce the notion of basis vectors. So when I look at this triad of vectors now, I will call them basis vectors, and in particular, I'm going to label them E1, E2, E3. And that is the notation that we will stick with for the rest of these lectures. Okay? So let's now begin to look at how all of this works out mathematically. All right. So as I just said, we are going to introduce these basis vectors, and I'll label them as E1. It's a vector, as is E2 and E3. All right. Now, directly, we're also going to introduce some shorthand notation for them. So instead of repeatedly referring to them as E1, E2, E3, we are going to introduce indices. Okay? And in particular, we are going to do the following. We have now introduced right here an orthonormal triad right? An orthonormal triad of vectors. Okay. In addition, these vectors are right-handed. The way we express this in our shorthand notation is the following. We describe these vectors as E sub I, okay? And there is a set of them which we denote by I running over 1, 2, and 3. The letter I is what we will refer to as an index. Okay? Now, I wrote out some mathematical terminology here. I call this an orthonormal triad of vectors that are right-handed. All of this can, of course, be put down in very precise terms mathematically, which we will proceed to do right now. First of all, triad, of course, refers to the fact that there are three of them, and there are three of them because we are doing things in three-dimensional space, right? Three-dimensional Euclidean space. Okay. Using this notation of EI, where I runs over 1, 2, and 3, we can now express these properties, right? We can express these properties of orthonormality and right-handedness. In particular, we can say the following, right? We can say that EI dotted with EJ equals a new symbol that we will denote as delta ij. Okay? This new symbol should be familiar to all of you. It has the following properties, right? Delta ij is equal to 1 if I equals j, and it's equal to 0 otherwise, right? Otherwise being if I is not equal to j. Do you remember what delta ij is conventionally called? Think about it for a few seconds. It's an easy one. You probably all immediately recall it. It is the Kronecker delta, right? So delta ij is what we refer to commonly as the Kronecker delta, sometimes called the Kronecker delta symbol. All right? Okay. And immediately you see what this means, right? You see that if I equals j, then we have the following sort of property, right? We have E1 dot E1, which is a particular manifestation now of I equals j. E1 dot E1 equals 1, and so on, right? E2 dot E2 equals 1, E3 dot E3 also equals 1, and E1 dot E2 equals 0, right? And so for E1 dot E3 and E2 dot E3. And immediately these properties tell us that the vectors, our basis vectors, are unit vectors, and furthermore that they are perpendicular to each other. Okay? And that leads to the term orthonormality. All right? Okay. We'll move on here. The other property I put down there was that of right-handedness. The way that works is the following. If we consider the cross product of these vectors, if we look at EI cross EJ, right, it is equal to EK, where here we are saying that I is not equal to J is not equal to K, right? So if we take a distinct set of those indices I, J, K, right, and we form these cross products, we get this sort of property, right? And now if we look at what this means in detail, this property, by the way, is what we call right-handedness. Okay, what does this mean in detail? Well, it means things like E1 cross E2 equals E3. Okay, and then if we continue, what it says also is that E2 cross E3 equals E1, and E3 cross E1 equals E2. All right. These are all probably very familiar to you, but it's useful to put them down. Now, note that even though we're using a right-handed set of basis vectors here, that is really a choice. Okay? It's a convention, it's what most people are used to seeing. One could equally well fully develop continuum physics using a left-handed system. Right? Things would look a little different, but nothing other than that. Right? It's just a matter of convention. All right, let's see now. Is there anything else I need to say about this? Not really, except I could probably go back to my little prop here of the basis vectors now, E1, E2, E3, and just observe some things, right? So we see that this right-handedness is what gives us our right-hand thumb rule as well, right? E1, E2, E3, we have E1 cross E2 gives us E3, right? Likewise, E2 cross E3 gives us E1, and E3 cross E1 gives us E2. Okay, those are just the rules we've put down. All right, now why is this introduction of basis vectors so useful? Okay, so let me put that down as a question. Why is the introduction of these basis vectors useful? Think about that for a second or two, and we'll pick up the answer right away. The reason it's useful is that now, when we have these basis vectors, it gives us a very precise way to describe our other vector, any other vector, right, as designated by this arrow, right? It gives us a very mathematically precise way to talk about any other vector, okay? In particular, what we can do is that any other vector, really any vector, can be expressed right in terms of the set EI. Right? I equals 1, 2, 3. In particular, if we think about our vector and we call it, let's suppose we call this vector u, we have a basis here. What it means is that we can now write it as u, the vector u, equals u1 times e1 plus u2 times e2 plus u3 times e3. The scalars u1, u2, u3 are called the components of u in this basis. Okay? So u1, u2, u3 are the components of u in the basis. All right. Now, as you can imagine, if every time we want to write a vector u, we write it in this form as u equals u1 plus u2, u1 e1 plus u2 e2 plus u3 e3, it's going to get a little cumbersome. Okay? We can do something better. Okay? So that better representation is the following. Observe that we could write u as a sum over I going from 1 to 3 because we're in 3 dimensions. It's a sum over I of u, I, ei. Right? This would work, except that, well, it's not so convenient because we have this new summation symbol here, which is a little clunky looking. Okay? A further simplification of notation, really, is introduced when we observe that really we can get rid of that summation symbol if we all agree that any time an index is repeated, it implies that we need to sum over that index, right? So we have the so-called summation convention over repeated indices. Okay, what this says is that now I can write u as simply ui ei, and for the very first time, and maybe even the very last time in the series of lectures, I'm going to put a little note here which says that sum is implied over I equals 1, 2, 3. What that means is that we read this not just as ui ei, but summing over I, right? So that is u1 e1 plus u2 e2 plus u3 e3. This convention, which you probably are all familiar with, also is sometimes called the Einstein summation convention. And the version of the story that I've heard is that in one of Einstein's papers, they ran into the same issue that we saw on this tablet, which is that the symbols were just getting too clunky and occupying too much space. So they just decided to drop the sums by looking at it and realizing that if the sum were implied and agreed upon, everything worked out. Okay, so that's the approach we will take. In very rare instances during these lectures, we will have to suspend this convention, and when we do have to do that, we will make it very explicit. Okay? All right. So we are here now. We have this way of writing out vectors, and let's observe that that this sort of representation is unique. Okay, this representation is unique. Meaning that given a vector u and a basis, there is only one way to write its components. Okay? And the way to see this is actually quite straightforward, right? The way we do it is the following. We consider the following, right? U is a vector, and so is EI, right? So we can consider their dot product, right? We write that out now as follows, right? We write this out as U, I, let me call it UJ, EJ. UJ, EJ is my representation of U, okay? The indices I, J, K are what we call dummy indices, so it doesn't matter whether I use I, J, K, L or something else. It's important in this particular demonstration that I don't use I again, right? So if I were to rewrite this as UI, EI, I would very likely get into some confusion because I already have an EI there, right? I've already used that index I there. So instead, I'm going to write U as UJ, EJ as done here, and then my dot product brings back the EI. Well, now I can expand this out, right? I see that I have UJ, EJ dot EI, but EJ dot EI, my Kronecker delta symbol tells me is UJ delta JI. Now we all know what that Kronecker delta does, right? It takes anything and it takes any other component multiplied by it and gives you back essentially the component with the index I on it, right? So all of this works out then to U sub I. And to see how that works, you could very well go back to this notation that we have out here, right? Simply expand out delta Ji and you will see that you end up with Ui. Okay? So what we're seeing is that given a vector E and a basis, right, out here, we see that the component Ui is defined very precisely as the vector U dotted with the basis vector EI. Okay? And this is what leads to the conclusion that this representation is unique. Okay? It says that our components Ui are unique. Okay. What we're going to do now to end this segment is to look at how the use of basis vectors allows us to write our dot product and scalar product. Okay? So, with the use of these basis vectors, how can we write our dot product? Okay? So, we in particular want to write the dot product of vectors u and v. Easy enough. We expand each of these guys. U is expanded as ui, ei, summation convention in use. Now v, we have to be careful. We don't use the index I again. That could lead to confusion. It will in fact lead to confusion. So we use another index, j. Right? Remember, these are dummy indices. Okay? So it doesn't matter what you use, long as you use something that's different. All right? Okay. Well, using all those properties of dot products that we know, this is just ui vj times ei dotted with ej. But ei dotted with ej is the Kronecker delta. We have ui vj delta ij. The Kronecker delta then does its job, which is to enforce the requirement that those indices have to be the same, right? Otherwise, the Kronecker delta reduces to 0. So we see that this basically gives us ui vi, summation convention in place, right? So ui vi is u1 v1 plus u2 v2 plus u3 v3. Also observe that the same thing would have followed if instead of writing this as ui vi, we were to have gone the other way, which is to write this as uj vj. Okay? Right? The other thing this lets us do is to say that, well, u dot u now is ui ui, which is ui square. Right? Well, if I wrote this as ui square, I would have to explicitly write out the sum because the indices are not repeated there, right? But that's why I prefer to write it as ui times ui. Okay, so this is what it does for the dot product. Let's look at what it does for the cross product, and we will be done with this segment. For the purpose of the cross product, we need to first introduce something that we will call the permutation symbol. Okay, we will denote it as epsilon I j k. Okay, and we are going to define this as follows, right? We are going to define this as epsilon I j k is equal to 1 if I j k are an even permutation it's equal to -1 if they form an odd permutation, and it's equal to 0 if any of the indices are repeated. Okay? And to understand what we mean by this, I just have to tell you what we mean by an even permutation. Right? An even permutation of I, j, k is something that I will write in the following fashion. 1, 2, 3. Okay? If ijk can be written as either 1, 2, 3 or 2, 3, 1 or 3, 1, 2, it is an even permutation. Okay? An odd permutation is I, j, k simply going the other way now. All right? And if it turns out that if either I or j or k represents a repeated index, such as if you have something like the index 1 has been repeated there, right? That's what I mean by repeated index. Okay? So all of these give us the different values of our permutation symbol. And then, what does this do for us for the cross product? Here's what it does. If we want to write the cross product of vectors u and v, right? This is written as ui vj times epsilon I j k ek. With your knowledge now of the permutation symbol, if you were to work out this formula, you would get back what you know for the cross product. Okay, we will stop here for this segment.